we present SOAC, Spatio-Temporal Overlap-Aware Multi-Sensor Calibration using Neural Radiance Fields. In our setup, we suppose that we have an autonomous driving car, rigidly mounted with multiple sensors of different modalities. In our case, we consider the most often encountered sensors, which are RGB cameras and LiDARs. The spatial calibration is the physical transformation in the 3D space between the sensors on the car. By supposing that this transformation is rigid, as we do, it means that if we know the position of sensor 0 at a given time, we can deduce the position of sensor 1 by knowing the transformation from 0 to 1. When an image or a LiDAR scan is captured, the timestamp associated with it might not match the temporal reference of the other sensors. An offset in the temporal calibration can cause a significant error in the position associated to the captured information. Thus, it is important to get the correct temporal calibration before exploiting the data. Thus, the goal of our method is to calibrate both spatially and temporally all the sensors on the car, as it is necessary to use the data provided by the sensors together for multimodal downstream tasks. In our previous work, MOIST, we used a single implicit scene representation and simultaneously optimized both the scene and the spatial and temporal calibration parameters of our system. However, this method didn't enforce the fusion of the information from the sensors, and thus allowed them to converge to local minimum. With our new work, SOAC, the calibration process is done with two different operations for each step: scene representation training and calibration parameters optimization. To each camera, we associate an implicit scene representation. During the scene representation training, the images from the cameras will train their respective scene representation. The LiDAR scans instead will both train the scene representations and optimize its calibration parameters. During the calibration parameters optimization step, the images from each camera will try to register themselves on the scene representation of the other cameras. This process enforces the information from each sensor to match with each other. However, as an implicit scene representation is trained by a single camera, the unseen part of the scene will only render noise, as we can see with a scene representation trained by the front camera. Thus, we introduce visibility grids, which are binary 3D voxel grids. We build a visibility grid for each scene representation, and their goal is to retain the information of which parts of the scene are trained. The filling is done during the scene representation training step. Then, during the calibration optimization step, the rays are filtered depending on if the scene is trained or not. Thus, we obtain a mask from the visibility grids that allows the filtering of noises. When looking at the results of spatial temporal calibration with MOIST and SOAC on Keys 360, we can observe that SOAC provides more stable results. And on new scene, the accuracy is much higher. When reprojecting LiDAR scans on the images according to the optimized calibration parameters, we can observe that SOAC offers correct reprojections, while MOIST has obvious mismatching between the LiDAR scans and the images. For highly dynamic scenes like the ones in Pandaset, an easy solution is to filter the semantic classes of potentially dynamic elements. Here, we show the benefits of such strategy, especially for the LiDAR. When looking at the LiDAR projections, we once again observe the superiority of SOAC against MOIST. Finally, for the specific task of LiDAR camera calibration, we compare our method against mutual information-based method by Pandy et al. And deep learning-based method LCCNet. The accuracy provided by SOAC is much higher across the dataset, showing the robustness of the method. By reprojecting the LiDAR scans, we can see the better alignment provided by SOAC. With SOAC, we provide a targetless, structureless, multimodal spatial-temporal calibration method which takes into account the overlap between the sensors for autonomous driving cars. We show the robustness of our method on 3 widely used driving datasets: KT360, NewScenes, PandaSet. Thank you for your attention.